Hello, good day. So we'll be discussing your binary number system here. So in this binary number system, we'll be discussing how we shall be using this binary number system, which is a part of your computer skill to for Tripura University, for whether you are a MA or MSc student who are taking up this computer skill 2 course, we will be studying binary number system. This lecture will be divided into two parts. The topics that we will be covering here are as under. The binary number system will be having conversion of binary number to decimal form, conversion of decimal number to binary form, addition of two binary numbers, binary multiplication, binary division, subtraction of binary numbers using 2's complement. Now we'll not be able to cover the whole thing in one lecture, so we'll be dividing this into two lectures. So let's start with what do you mean by a number system. Number systems we are using, normally we are all using decimal number system, whether you are you writing in Hindi, Bengali, English. So this is the normal symbol based number system. You can see this is a symbol. Yeah, I have written the symbols in English. So obviously the same thing, you are having a symbol as English. Now in Hindi and Bengali we are having the same thing. So the difference is that how you write a one here and in English, Hindi or Bengali. Now let's look into the symbol in Roman. Now there is difference here. Here you don't have a same thing as this. The one may be same, but when you go for two, you have a different symbol. Three, you are having a different symbol. But once after 1, 2 and 3, when you go to 4, what you are having the symbol of 5 and the symbol of 1. Actually you are doing 5 minus 1 and getting 4. 5 again is having an individual symbol, but 6, 7, 8 are not having individual symbol. Neither does 9 have an individual symbol. 6 is 5 plus 1, 7 is 5 plus 2, 8 is 5 plus 3 and so on. And 9 is 10 minus 1. Same thing you can see here. For 2 it is 2 ones, 3 is 3 ones and so on. Now what happens to this number system when we cross this number 9? All of you know that these are positional number systems, whereas this is a non-positional number system, because here the positions do not matter. Why? Because you see here the position here for the 0 to 9 symbol, as it is in English, Hindi or Bengali, is similar. Just we are having separate 9 symbols here, 10 symbols here, starting with 0 to 9, where in Roman we don't have a symbolic positional number system 1, 2, 3 here, because we are not having similar kind of symbols. So normally it is called non-positional number system. Y will come here once we go to the 11th number. In this 11th number, what happens in English, we are having again 0 to 9 with the red colored ones coming. In Hindi also same, Bengali also same, because these are positional. In Roman we are having 10, 10 plus 1, 10 plus 2, 10 plus 3, 10 plus 4, where 4 is again 5 minus 1. Then 15 is 10 plus 5, 16 is 10 plus 5 plus 1. So we are not having a similar kind of thing. We are not having equivalent number of symbols in each and every number. Here, let's go for a sudden number in 38. So this 38 is same here, but when you see here the symbol for Roman is totally different. Now 50 is having a different number in Roman, 60 is 100 is having a different number, and 1000 is having a different number. But in positional number systems that we have, we are having same kind of things. The position is based on the position, you know the number. So these are decimal number systems, all of them. Whereas this non-positional number this positional number system, what we are seeing in decimal, here what we have the three things. The symbols represent different values based on the position of the symbol. The values of each digit is determined by the digit itself, position of the digit, and radix, which is the base of the number. Let's take an example. 1125. So this is, in decimal, and here I've written 10, means it is a decimal number system. So in decimal number system, you know that we are having 10 symbols, 0 to 9. So it is only 1125, where 1125 are the digits and 10 is the radix, and these are the index of the positions. What is this value? Same thing if we take, but just difference between these two is the radix is 8. Now when the radix is 8, that means we are having 8 symbols. So if we have 8 symbols instead of 10, that means we are having, instead of 0 to 9, we are having 0 to 7. So the symbols 8 and 9 do not exist in radix 8. Now what about the values of these numbers? For the first one, the 5 is 10, 5 into 10 to the power 0, 5, 2 into 10 to the power 1, 20, 1 into 10 to the power 200, and 1 into 10 to the power 3. So together when you add up, it is 1125, which is 1125 in decimal system. So both are decimal systems, so obviously it will be same. But that is not the same case when you convert a radix 8 system to decimal. Why? Because here 5 into 10 to the power 8 to the power 0, 2 into 8 to the power 1, 1 into 8 to the power 2, and 1 into 8 to the power 3. So this is 597. So the same 1125, if you write base 10, is equal to 1125, whereas this 1125 when you write base 8 is actually having a value of 597. So what are these kind of number systems, positional number systems being having different radix? These are the different number systems. For decimal, you already know is 0 to 9. For hexadecimal means it is 16. So you have 16 symbols. So after 9, you are using A, B, C, D, E, and F, the 6 extra symbols. For octal, obviously, we'll be having 2 less. And the popular one, which we are discussing now, binary, is 0 and 1. Means only 2 symbols. And this is what we are having in normally a switch, which is on or off. 0 and 1, you can use them as on and off. Now let's go to popular positional number systems. The popular positional number systems are base 2, which is binary, quinary, which is base 5, octal base 8, hexadecimal base 16, and obviously the base 10 decimal, Now you see the numbers. For base 10, 0 to 9, then 10, 11, 12, 13, 14, 15. For binary, it is 0, 1, 1, 0. So as we are having two symbols, so it's the same thing. Just repeating. Here we had, after completion of 10 numbers in the 10th value, the 11th value is having the position increased. Here we don't have that. So the position increases from 3 onwards. So the third symbol is 1, 0. Then 1, 1, 1, 0, 0. Though the value of 1, 0 is actually 2. So you are having 0, 1, 2 valued as the first, second, and third number. So when you are having a binary number system of base 2 and you are having only 2 bits, you have 0, 0, 0, 1, 1, 0, 1, 1. These are the 4 numbers possible with 2 bits. You go to base 5, the same thing, 0, 1, 2, 3, 4, and after that 1, 0 again. Base 8, 0, 1, 2, 3, 4, 5, 6, 7, and then 10, 11, 12. And hexadecimal, you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, followed by A, B, C, D, E, F, which are coming. Now, this base n means n is whichever radix you are having, number system, where you are having 0 to n minus 1. For binary, base 2, you are having 0 and 2 minus 1 is 1, so 0 and 1. When it is base 10, you are having 0 to 9, base 8, 0 to 7, and so on. So this 1045, if it is a number with n, we have positional number system, and this positional number system having d0 is the least significant digit and dn minus 1 is the most significant digit. So n minus 1 n to the power 4, n to the power 3, so on, you will be having up to n minus 1. The digit numbers are here. Now the formula here is n is equal to biq to the power I, where n is a real positive number, b is the digit, q is the base value, and integer I can be positive, negative, 0, and so on. The binary number system is having base 2, n equal to 2. So we will be starting the binary number system from here. We are having 0 and 1. The example is 10101110. Just a random number that we have taken. This is a positional number system, and we are having binary digits. So in short, it is called bits. So we are having the 0 and 1, which are called bits, and these are having B0 as the least significant bit, and Bn-1 is the most significant bit. So 2 to the power n, just like earlier, and Bn-1 to 0. The decimal number system on the same lines is having 0 to 9. This example is 1045 base 10 position number system, and so on. Only difference is that here most significant bit becomes least significant digit, and most significant bit becomes most significant digit. So the same thing. Now conversion of any binary number to decimal form. We know that n is equal to biqy. This we have already discussed. Here the integer I can be positive or negative. Let's go to the negative part later on. We will be discussing in the later on lectures. Here binary decimal is to convert base 2 to base 10. Now in general, from our childhood we are accustomed to the decimal system where n is a real positive number which is varying from 0 to 9. So here what we have to do is that we have to convert this into a binary number system, and b equal to 0 and 1, here q equal to 2, and I being the position. So let's take the binary number system and convert it to decimal. So qi, which is having the powers of q, the lowest, say let us consider 8 bits, which is very common. We are having most of the things in 8, 16, 32. These things we will be discussing later on. But let us consider a system having 8 bits where it starts with 2 to the power 0 and with 2 to the power 7. The decimal digit values for these are 1, 2, 4, 8, 16, 32, 64, 1, 2. So it is similar to 1 being double to 2, 2 being double to 4, 4 being double to 8, 8 being double to 16, 16 being double to 32, and 32 being 64, and so on. Let us take some random binary digits 10101010 like this. Now let's get the value of this. What is the value? The formula is same, and we get 128 because 1 into 128, 0 because 0 is multiplied here, 32, 0, 8, 4, and 0, 0, 2 and 1, 2, and 1 and 0, 0. So this 10101010 base 2 is equal to 170 if you add them up. To just expand, you can see this is what we are doing. If you add them up, you get 170. So the value of 10101010, that is this 8-bit number in binary, is actually equal to 170 in decimal value. Now let's go for the other way around, conversion of a decimal number to a binary form. How to do that? We have to do repeated division by 2 method, where we have 294 as a random decimal number. We want to convert it. So we have to do repeated division and get quotient element. So let's start this, and the remainders that we will be getting will be used to get the binary number. 294 base 10 equal to first divided by 2. So 294 divided is 147 and the remainder 0. So this 0 is the less b, which comes here. Next, again we divide 147 divided by 2 is 73, but now the remainder is 1, which will come here. We go on, and now 73 divided by 2 gives 36 with the remainder 1. It comes here. 36 divided by 2 gives 18, which remainder 0, which comes here. Then 18 divided by 2 is 9, which remainder 0, comes here. Again 9 gives 4 and 1. Then 4 gives 2 and 0. The 0 comes here. And 2 gives 1 and 0. And again when we divide this, we get 0 and the remainder 1. And this one is as after that the result is 0. So the last bit is the most significant bit. So when you take this 294 to this digital number and you expand it, so you are having 256 plus 32 plus 4 plus 2 patient positions. So 1 into 2 to the power 8 is 256. 1 into 2 to the power 5 is 32. 1 into 2 to the power 2 is 4. And 1 into 2 is equal to 2. This is how you convert a decimal number to a binary form. So here I give you a break from this lecture, and we will start another lecture in the next class. So this is all for now. We'll continue with the binary system soon, and we will continue the binary system in the next lecture. So stay tuned for the next lecture.